So we're all set. All right. Okay. Welcome to robotics seminar. Today we're extremely happy to have our very own ex-Robograd, Derek Hoiem, coming back to give us talk about what he's been up to. Derek has finished, graduated from Robotics Institute in 2007. He was working with Marcel and myself. He did an extremely cool thesis on understanding qualitative 3D structure and modeling the stuff within a single image. That thesis has received the CMU Best Dissertation Award last year. And so we are very happy to have Derek back. He's now assistant professor at the University of Illinois Urbana-Champaign. We have asked him to, Derek has done a lot of very hardcore, detailed work, and a lot of us already know that stuff. But so we asked Derek for this time to maybe do something more long range and philosophical, and talk about kind of more of a new directions, maybe not something that's completely worked out, but talking about some kind of a new exciting direction. And I think this talk is going to be perfectly fit this. And also, we thought it would be a very good idea there is a lot of Robograds here. There would be a very good idea to have Derek talk just about for a little bit about the transition from being a Robograd to going out into the real world. So I think he'll do that for a little bit as well. So we're very happy to have Derek here. Derek?
Thank you. Yeah, I don't know if you can call that the real world, but it's a different one. So yeah, it's very nice to be here. It's very nice to see a lot of familiar faces and even more unfamiliar ones. Oh, and this work that I'm going to describe in a moment is it's work with two very excellent students, Ali Farhadi and Ian Andres, and David Forsyth, who's a great collaborator. So first I'm going to just spend a couple of minutes just mentioning a couple of things about transitions. There's two transitions that I had to make. One is going from the Robotics Institute here in Pittsburgh to the University of Illinois in Champaign, and the other one is transitioning from being a student to a professor. So I'll just mention a couple of things, and if any of you are graduating students and are wondering what it's like to be a new professor, or if I have any advice, you can feel free to talk to me during the PSR. Okay, so the first thing, which was a major change, was the change in my perceived magnitude of AI and vision. I think no matter what, when you're doing a PhD, I think you start to get a more and more focused view of what computer science is and what the whole research world is in general. And so when I'm here, when I would talk to somebody, if somebody would say, I'd say, what do you do? And they say mobile robotics. And I'd think, oh, that's not even related to me. You're like the 50th closest person to my research. And that's not going to be true in most universities. We have such a huge AI community here and a huge vision community. So this is kind of a representation of how many people. This is partly my work perception due to being in robotics, but it's fairly accurate in many ways. And that as a robotics student, there's computer science, and you can get rid of maybe like 50% of the people, and then you're left with AI, and then narrow it down a bit more to graphics and other things that are vaguely related to me, and then computer vision. But this is still like a huge chunk of the overall pie. And in computer science at UIUC, it's just a tiny little piece. And that struck me the most when I went to my first prospective student. I talked to the prospective students. And time after time, I'd ask them, what are you doing? And they'd say, oh, I'm doing systems. I'm doing programming languages. I'm doing architecture. And those things, I hadn't talked to anybody who did any of those things in 5 years. I didn't even know it was still computer science. So that was a huge change, and it has its pros and cons. So this was my perceived. This was vision before, and this is vision after moving to UIUC. I realized that we're a much smaller part of the world than I had thought. So then the other change was to being a professor, and here I'll just give a couple of pieces of very broad advice. One thing is to remember that your role is to guide and teach, and that's something that's hard to remember. As a student, you're used to having a lot of control. Basically, whether the project succeeds, your advisor has some role in that, but ultimately it's in your hands. You're doing a lot of the low-level work, you're writing a lot of the paper. And as an advisor to somebody, it's not your job to make sure they get everything perfect. It's your job to make sure that they learn the skills they need to be independent and to work on their own. And that's something that takes a lot of getting used to. And because of that, I would recommend that if you can, to co-advise your first student. I learned a lot by, I co-advised a student with David Forsyth, and I've learned a lot by sitting in by doing that together and watching how he reacts to the student. And sometimes you have to one of the things that I learned is that sometimes you have to let the student do the wrong thing and learn that it's the wrong thing. You can't always browbeat them into doing what you want. So I can talk more individually if you're interested in hearing about this stuff. So now I'm going to talk about research. And ultimately, the goal of computer vision is to make useful inferences about scenes from imagery. So take this scene, for instance. We could ask, what do we want to know about this object? Now, if you ask a researcher in object recognition, they'll say, well, what you want to do is to be able to say this is a dog. But if you ask somebody in the scene, they're going to give you a totally different answer. They're going to say, like, I don't care that it's a dog. I want to know that it's large, it has pointy teeth, and it could bite me. That's really what this image is. So our goal here is not to infer the names of things, but to infer their properties. We might want to be able to tell what we can do with it, or what it can do if it's something that's alive. We might want to know some of the material properties. Is it made out of wood? If we want to pick it up, we might want to know the shape or the weight, or how shiny is it, and so on. And we want to be able to do that even if we don't know the name of the object, even if it's something that we've never seen before. So why do we care about properties? One reason is that we want detailed information about objects. The name just doesn't summarize the picture. A second thing is that we want to be able to infer something about unfamiliar objects, and this is probably the most important reason. If we take a standard recognition approach and we know about cats and horses and dogs, then when we see these images, then we'll be able to say cat, horse, and dog. But when we see this image of some object that we've never seen before, we won't be able to say anything. All we can say is that it's not a cat, it's not a horse, and it's not a dog. On the other hand, if we infer properties from these animals, then when we see some new object, we still don't know that it's called a zebra, but at least we know some things about it. We can say it has stripes because we've seen other things that have stripes. It has a mane and a tail like the horse, and so on. The third reason is that we want to be able to make comparisons between objects and categories. Not all dogs are the same, so we might want to say, what's the difference between two dogs, or how is this dog unusual? And two things in different categories can have many similarities. So we want to be able to reason about things not in terms of black and white categories, but in terms of having differences and similarities to each other. So there's three strategies that we could use to infer these properties. The first one is through category recognition, and this is a form of what's in psychology is called mediated perception. Here you have a picture of the object, and then you have a classifier that you can use to attach a name or a category to it, in this case a car. And then you say, okay, because it's a car, that means that it has 4 wheels and it can be used for transportation and it's made of metal and so on. Of course, the disadvantage of this is that all you get from the category are the properties that are typically associated with it. And it doesn't necessarily apply to this specific instance. A second form of mediated perception is exemplar matching, and this is best exemplified by Tomasz and Alyosha's work. Here, instead of having a set of categories, you just have a whole bunch of instances, and you have properties that are associated with those instances. And in a sense, everything you've seen is its own category. And so you can say much more specific things about the object by finding the most similar thing you've ever seen, and then attaching whatever properties you have from that instance to your new example. And so in this case, maybe you could look at this and say that it's old in addition to the usual properties of cars. But this still has limitations, because unless you've seen something before that has exactly the same properties of what you're looking at now, then you're going to make a lot of mistakes. And but I'm just going to digress very slightly into a way of avoiding that problem. So that's only true if you have one way of matching. If all you can do is say that x is similar to y, then you need to have seen something very similar. But if you can say that x is similar to y in this sense, and x is similar to z in a different sense, then you can infer similarities. You can say that something is similar to different objects in different ways. And we've got some recent work on doing this, where we learn similarities by looking at photo sharing sites, where people have shared on Flickr billions of images, and they group these images into hundreds of thousands of groups. And we've created a very fast online training method that we can use to say what group an image is likely to belong to. Then we can say not only that two images are similar, but how they're similar. So in this case, I'll show a couple of examples of how of two images that the system thinks are similar, and the ways that it thinks they're similar. So the two images are on the left, and then these words are how it thinks that they're related, and then the numbers are the confidences. So it thinks that these have something to do with fireworks or Christmas, rain, water, or candles. These it thinks it has to do with sports, dances, weddings, toys, and horses. So it's not always right, but this is much more informative to give this kind of similarity information between images than just saying the similarity is 0.3. Here it thinks that these are similar in the sense that their paintings are macro flowers that are far away, hands, or skateboarding. And that was kind of puzzling at first, and then I think it was my wife pointed out to me the pose of the person on the left there.
Are those from pre-existing categories or volunteered?
They're from pre-existing categories, but there's a huge number of categories. And the categories can be things like love and abstract, and they're sort of all different things. Okay, so those are two strategies. The third strategy is different. It's to infer the properties directly. So you have an input image, and then you try to directly predict the properties of that object. So this is really the only way that we're likely to be able to say that this car doesn't have wheels, because we see that there aren't any wheels there. There's also a related work to this in the same conference in CVPR 9. And again, this idea is an old idea in psychology. It's affordances, and it's more generally called direct perception. So there's these three strategies. And there's been a lot of work in this first one in category recognition, although we don't really know how useful it is for inferring properties, because almost everybody just stops at the categories. There's been some more work in using in doing this exemplar matching and then transferring associated properties, but still not too much in that area. But almost no work in this area. We try to learn properties from some set of objects and apply it to a new set of objects. And so this third strategy is what I'm going to focus on here. So these are the kinds of attributes that we're going to try to learn. There's parts, there's materials and material properties, and shape. And our definition is slightly peculiar in the sense that we'll say that we're trying to say what parts or materials are actually visible. So we would say, this has a wheel and I can see it, or I can't see that this object has a wheel. And parts could be things like wheels, snout, eyes. Materials could be like made of metal, made of plastic, made of glass, or shiny, or furry. And shape could be things like 3D boxy, or round, or cylindrical. And there's 64 attributes in all. So here are some examples. So these are, if we see these images, this is what we would want to be able to infer about it. In the airplane, and these are from people's annotations. In the airplane, this is described as being a horizontal cylinder. It's got wings and a propeller and window and wheel. It's made of metal and glass. The car, there's no description for the shape. It's often hard to provide some kind of verbal description for shapes. It's got window, wheel, door, headlight, and so on. It's metal and shiny. And then likewise, for other objects, we can describe them in terms of their parts and materials and shape. So a person, we would say they have skin and cloth. A cat is furry. And this picture of a cat has a head, an ear, we call a snout, this area, and an eye. So this is what we want to be able to infer when we see an image, and we want to be able to infer this for new objects.
So it seems clear that people are assigning these, and they're doing a categorization, whether you expect that or not. Otherwise, they'd say headlights in the middle one. But that doesn't come up because they know it's not that kind of thing.
Why would they say headlights?
Well, if his eyes are open anyway.
If they
headlights or
Headlights. or wheels for something that...
You could think of these attributes as a kind of category that spans what we tend to think of as basic level categories. So it's you can sort of think of it as that there's cross sections of categorizations. And so you can learn one cross section and then generalize across the other one.
If the categories are purely perceptual, not deriving from a category, if the attributes are purely perceptual, not deriving from a category, that's fine. You can build filters for those or something, but it doesn't look like that's what the people assigning them is doing. They're doing the category whether you want them to or not.
Right, they're not, right, these aren't purely perceptual things. There's not necessarily a one-to-one mapping between image features and these things that we're trying to infer. That's true.
So what is your goal? To do bottom-up perception, or to say it's a cat, and now I'm going to verify it has all the parts the cat is supposed to have?
My goal is to use as much information as I have to say as much about the object as I can. So if I'm familiar with cats, then I can say much more. I can also say it meows, which is something I'll never figure out by looking at the cat. And if I see it's a cat, then I know certain things about it, and I'm going to say it has 4 legs unless I have visual evidence to the contrary. So there's all these different strategies are all valid. Here I'm focusing on direct perception, not because I think that that inferring these attributes from categories is the wrong thing to do, just because it's the only thing that people have focused on so far. Does that make sense?
I think that Scott's point is that it's not all that direct. I mean, the parts that are attributed are restricted by knowledge of the category that it's coming from. So of a human, you might say skin, right? Of a chair, you're not going to say skin, and yet perceptually, the material covering a chair might look enormously like, and in fact it might have been skin at some point, but in any case it would look a lot like the material that's covering a person's body, but in one case you call it skin, in the other case you call it cloth. That's coming out of mediation, it's not coming out of direct perception.
Yeah, I guess what I mean is that, well, okay, so yeah, I see. So you're sort of saying that in some sense you wouldn't necessarily use the same words to describe even the same. There's a difference between the material of a skin and the material of the chair. So
division, I could easily.
No, there's a difference in the hardness and material. They're different materials. That's what I mean.
Something like shiny is purely perceptual.
Right.
Or round, meaning round the whole thing.
Yeah. So
something like snout is I think pretty influenced by the category you think you're in.
Yeah, I wouldn't argue with that. So the goal is to have shared descriptions of objects so that we can generalize to new ones. So there aren't any data sets on this for vision, and so we did some collection. We collected 2 kinds of data sets because we're going to want to learn about these properties from some objects and then infer them in different kinds of objects. So the first data set, we just took an existing object recognition data set and added annotation labels. So we used the Pascal 2008 data set, which has 20 objects, mostly animals, vehicles, or some things. And then we assigned ground truth attributes using Amazon's Mechanical Turk. So that's like this. There's this system where you can pay people to do stuff for you, and there's about 300,000 labels that we needed, and it costs about $600 to do it. So it's kind of a useful labeling tool. The second data set is from Yahoo. So we collected these images in a different way. The Pascal images are collected using Flickr, and so they have certain kinds of data set biases and then certain attribute correlation biases because they're a limited range of objects. These Yahoo images were chosen to be of objects that share some attributes with the Pascal ones, but may have different correlations among those attributes. And the images that you typically find with this in this way will have different biases than the images that you find from Flickr. So one issue is that the attribute labels are somewhat ambiguous. Like whether you call shiny is really a matter of degree, so different people might disagree whether something is shiny. Or if you have something like made of glass, if some tiny part of it is made of glass, one person might say it's made of glass and one person might not. So overall there's about an 84% agreement among experts who are the authors or among the labelers that we hired to do this. So this is our approach. We have an input image and we do a special kind of feature extraction that I'll explain soon. And so we have some features that we think are useful for each attribute. We train a classifier, make predictions about the attribute, and we can use those predictions to describe this particular object, or we could use those attributes to try to say what category it's in. And for features, we're not doing anything very clever. We're basically trying to cover our bases. So we have color and texture features that are useful for classifying materials. We have histograms of edges that are useful for characterizing shape. And we have a histogram of gradients, which are quantized, which are useful for figuring out what parts an object has. So we're going to try to learn to distinguish between things that have an attribute and things that don't. And we're going to train one classifier per attribute. The simplest approach to do this would be to train a classifier using all the features for each attribute independently. So if we did it this way, we would back up all the examples of things that have wheels and all the examples of things where no wheel is visible. Now, if you look at these, you'll notice that's not the only difference between these images. Things that have wheels also tend to be made out of metal for the objects that we have, and there may be other things that they have in common that are other differences between these. And so if we think that there's a problem in that many of the attributes are strongly related through the object category. So when we think we're learning has wheels, we might actually be learning something to do with made out of metal or some other thing that just happens to be correlated with that. And so there's a danger of getting these different attributes confused. And then when we see something that has wheels, we might think it's also made out of metal, just because we never really learned what we intended. The way that we deal with this is by selecting features that can distinguish between two classes. The first class are things that have an attribute, and the second class are things that have other attributes in common, that have many similar attributes, except for the attribute that we're concerned with at the moment, except for the target attribute. And then once we select these features, then we can train a classifier on all the positive and negative examples using these features. So for example, if we want to learn the attribute of wheel, we would rack up the examples of cars where we can see the wheel and cars where we can't, boats where we can see the wheels and boats where it doesn't have them or we don't see them, and so on for all the objects that could potentially have wheels. And then for each one, we can select the features that are useful within that category for predicting whether or not it has this attribute, in this case wheels, and then pull those features and use only those features to tell whether or not something has wheels. And so in this case of has wheel and made of metal, in the original data set that we're using for the original objects, there's a 0.71 correlation between the attributes of wheel and metal. In the other data set that we collected, that correlation is much weaker. It's 0.17. And so if we use all the features that we started with, then when we predict these attributes on the new data set, we get a much larger correlation than is actually in the data set. So that means that we've actually confused these concepts, these attributes of wheel and metal. But when we do this special kind of feature selection, the correlation of our predictions matches the correlation that's in the ground truth of the second data set much closer. So now I'm going to talk about a variety of things that we can do once we can predict attributes and show you some examples of how that works. So first I'm going to talk about how well we can predict attributes for objects that we've never seen before. And then how we can use these to learn new categories, either from a small number of limited examples or learning from verbal description alone. How we can identify what's unusual about an object. And then I'm going to talk about a series of tests that we did to try to provide evidence that we really learned what's intended, not just something that's correlated with it, which is a very tricky issue in general. So for predicting attributes, we train on these 20 object classes from one data set. For each attribute, we do the feature selection, train a classifier, and then we test on a different set of objects from this other data set. And so it's a cross-category and cross-data set kind of generalization that we need. So first I'll show some qualitative examples. These are, it sees like what's in the bounding box here. So it's asked what is, describe this object for me, assign the attributes that belong to this object. And then we randomly chose 5 attributes that were assigned to the object. It might be assigned more in some cases. So like for this skyscraper, it's never seen skyscrapers, but it says that it's 3D boxy. It says that it's a vertical cylinder, which actually isn't right. It says that it has windows and rows of windows, which are things that it's seen. It's seen windows on cars and airplanes and rows of windows on 747s. And it thinks that it has a headlight. It looks at this bag and it says has hand and arm, which is it's getting confused with other objects that happen to be in that box. So it's not segmenting out the object correctly. It also thinks it has a screen, and it says that it's made of plastic and is shiny. It looks at this centaur and it says it has a hair and face. It thinks it has a saddle, which it doesn't, and that it has skin. And none of these examples were seen during training. So that's something that's I think that's kind of new, is that you can see something that you've never seen before, and you can still describe it to some extent. So here's some more examples. It looks at this cart and it says it's boxy and has a wheel and a window. It looks at the zebra and it says it has a tail and snout and leg. It also thinks that it has text, which is probably because when it sees something black and white, it associates that with text. And it thinks that it's made out of plastic, which is probably because of it's kind of got some specular reflections. So we can also look at this quantitatively. The red curve is showing how well we can predict these attributes for new objects, for objects that we haven't seen. And the blue dots are showing how well we can predict these attributes for familiar objects. So in the case of the blue dots, we train on the train set in this Pascal, for these Pascal objects, and test on the test set for those same objects. And in the red case, we're testing on new objects. So as you would expect, you can make better predictions. You predict things more accurately for familiar objects, even when you're not using the object category information. But you can still do fairly well. There's not an enormous drop-off. We can also look at the things that are difficult to classify. So what's reported here is the area under the ROC curve for each attribute. Things that are difficult are things like wings and handlebars, which tend to be fairly small. Like a lot of times when you see the wing of an airplane, it's facing you. Leather, clear, and cloth. And it's good at telling whether or not something whether you can see something's eye, side mirror, torso, head, or ear. So in general, parts tend to be easier. So we can also break it down into parts. And it tends to be easier to identify whether or not something has a part than what it's made out of or what its shape is, which is kind of reasonable to expect. So now we'll look at how we can use these attributes to do category recognition. And for this, the semantic attributes, what I call the semantic attributes, aren't enough to do this task well, because it's difficult to verbally describe the difference between, say, a cat and a dog. We use many of the same words to describe them. And even if we use the ground truth attributes, we can only categorize among these 20 Pascal classes with 74% accuracy. So we also create a different kind of attribute, which is something that doesn't have a clear semantics, but is useful for discriminating between objects. And the way that we create these is we select subsets of classes and a subset of features and train a classifier that can distinguish between those classes based on those features. So it might be something like tell the difference between dogs and sheep using color, or tell the difference between cars and buses versus motorbikes and bicycles using edges. And we create a whole bunch of these classifiers, and then using a validation set, we can determine which of these discriminative attributes are reliable. So to do the categorization in this case, we use the attribute predictions as features, and then we train a classifier to categorize the objects. And the attributes aren't a big help in this case. If all you want to do is to be able to name objects that you've seen before, then really the best way to do that is to learn that task directly. So if we have the base features, is if we just use all the features that we're using to learn the attributes. This is if we only use these semantic parts, material, and shape attributes. And this is with the discriminative attributes. So we're getting slightly better accuracy when we try to do this categorization, but it's really not a big difference. So the reason to learn these attributes is not to predict categories. It's the other way around. We want to learn categories to predict the properties of the objects. We can also, though, we can more efficiently learn new categories if we have this ability to identify properties. So if we have a limited number of examples, the way that we do that is by nearest neighbor prediction based on the predicted attributes. And we can also identify categories based on verbal description. In that case, we would say something, we'd identify the attributes of an object category, like say that goats have legs and horns and head and torso and feet and is furry, and the same for the other categories, and then try to categorize based on the predicted attributes in this description. So here's what we get. So this, on the x-axis, is the number of training examples per category. And on the y-axis is the accuracy and prediction. And this blue line would be if we just use the original image features. The red line is if we only use semantic predictions and do nearest neighbor. And the dotted black line is if we use both the more semantic attributes and the discriminative attributes. And I think the two things to note are that using this combination of attributes allows you to learn more quickly and more effectively about new categories than using the base features. But I think the most interesting thing is this, which is that from a purely textual description, you can now categorize well above chance. And you can get, it's about 33% accurate, where chance would be 8%. And you can do as well based on a textual description as if you had 8 visual examples with the original features. Mm-hmm.
So you have a very nice story for these descriptive attributes. But the discriminative attributes, what do they capture? What do they mean?
That's why we call them discriminative instead of semantic. I'm not really sure what they mean. I mean, we know what they're trained to do, but they don't have any attached semantics to them. So they're just sort of, I guess you could think of it as just a way of, it's like a hidden layer representation almost. It's just a combination of the features that's been learned to be useful for classification in general. We only use those for the categorization.
Following on in this vein, I'm getting increasingly nervous that all these features are verbal or linguistic. And especially when you start saying, well, they're like hidden neurons or hidden layers. Shouldn't they really be something else? Maybe samples of textures or arbitrary vectors you compute? So you can do operations on them. This furry business. I don't know what furry is. Mm-hmm. I bet the labelers don't know what furry is either.
Some things, one thing that's a little strange about our labeling is that things like furry and shiny and other things that we're not doing like size are matters of degree. So it makes more sense to say, some things it doesn't make sense to even say, is this furry or not? Some things you can say, my sheepdog is more furry than your hairless cat or something.
Compute something from the image and never have a human being involved?
If you want to do fully automatic computer vision.
Well, no, if I want to do accurate, if I want to make this better. It seems to me these verbal labels are going to kill you in the end.
In what sense?
Because there's so much semantics loaded into them that your labelers are perceiving, and ultimately you are perceiving. And so to say, well, this is really our hidden layer of a neural network or something like that, can't possibly be true.
Well, the semantic, so there's the discriminative attributes, which are kind of weird, and the semantic attribute, what I call the semantic attributes, which are these ones that we're learning by supervision. And so you're saying that the semantic attributes, there are still all sorts of things associated with those attributes. Those attributes themselves are kind of fuzzy, so it's weird to be trying to predict them. Is that what you're saying, or?
You're solving a vision problem, and you're going linguistic basically in the first step. And I would argue you might be better off if you went linguistic at the last step.
I think, yeah, that's a good point. It's actually something that I've thought about a lot. Like, so there's this idea of grounding vision or grounding perception, and there's a question of like whether it makes sense, whether you can possibly do that without having a physical agent, say, or some real physical, tangible basis for making links between what you see and how that involves your ability to solve goals. I think that by going to a verbal description, we don't get all the way there. Like you couldn't use this and learn how it would feel to touch something. But I think that this is still a very useful way of trying to deal with vision, because it avoids dealing with all the machinery and other aspects that I think right now would bog us down much too far, and allows us to get at some interesting properties of vision. So
I guess I have a kind of question maybe for both of you. So I think the reason that this makes sense to me is it's a way of organizing your data, right? More than it's that you're trying to learn this particular label, you're leveraging human expertise to tell you which images have interesting correlations. I could maybe I call it furry, or maybe I can just call it label 47. But there are a bunch of images that share label 47, and so now I can look for those. What things correlate with label 47, and not all the other labels. And that in some sense to me is one of the very interesting things about what you're doing, is that you're just trying to find a way to get people to tell you how to organize a bunch of images so that you can try to find patterns in them. Because otherwise you're just looking at all of the images in Flickr and thinking to yourself, well, I don't know what the hell to do. Just run a bunch of filters over it and hope for the best that they'll fall into categories?
So Japanese as a language has very few words that talk about agility. So if you asked a bunch of Japanese to label a bunch of pictures in Japanese, you're going to get a huge bias because of the structure of their language. you could argue that's a good thing. I fear it.
No, I agree. It's something that I think about a lot. But I think that this is a big step away from just thinking about things in terms of categories. And if two things are in the same category, then they're identical. And if they're in different categories, then they're completely different. So another thing that we can do is identify unusual attributes. So here we are like predicting the class of we're predicting the class of an object and then predicting its attributes, and then reporting if an attribute is not expected given the class. So we can do it in two ways. One is to report attributes that we expect that we don't see. So here are some examples of that. And in total, there's 752 times that it reports seeing an unusual attribute in this sense, and 68% are correct. So it thinks this is an airplane that doesn't have a wing. And really what it means is I can't see a wing. So I see an airplane, I would expect to see a wing, but I don't see one. Or here it says this is a car that doesn't have a window. This is a boat that doesn't have a sail. This is an airplane that doesn't have a jet engine. And in some cases it's wrong, like it says this is a motorbike that doesn't have a side mirror, but it does. Or this is a car that doesn't have a door. Here's kind of my favorite example. This is a sheep that doesn't have wool. I think it was probably lucky. We can also report the presence of an attribute that we wouldn't expect but is there. So it looks at the motorbike and it says, there's kind of three cases. One case is that it's right. It looks at the motorbike and it says it has cloth on it, which is true. It says this person has a label, which is what he does on his jacket. And then there's other cases where it sees other objects that are nearby and confuses them. So it says this is a bird that has a leaf. This is a bus that has a face, because it sees there's faces in the image. And then the third case is where it's not right, but it sort of tells you something about how the object looks. So it says this is an airplane that has a beak. And that's kind of a common mistake, is to think like airplanes or jet skis have beaks. It thinks this is a sofa that has a wheel, and it doesn't, but it has these things that kind of look like wheels. Or this is a bike that has a horn. And because the handlebars kind of look like the horns of sheep. So now a really big issue is how do we know if we've learned what we intended to learn? And this is an issue that affects all of pattern recognition, really. And it's something that I think with large data sets we've been sort of lured into a false sense of security, because there's a feeling that if we have enough data, then we must have enough variety, and so we can ignore this problem. But both data set biases and natural correlations can make us feel like we have a well-learned model, when in fact we've only learned something that's correlated with it. So how can we tease out this? How can we figure out if we've actually learned what we intend? So we do this for this task, and then after I go through the examples of how we've done it, then I'll summarize some of the ways. So I think we have fairly strong evidence that when we're predicting an attribute, the classifiers are actually predicting that attribute and not just something that's correlated with it. And one way that we can tell that, or at least that this form of feature selection improves our ability to do so. One way to look at it is by the unusual attributes that I showed earlier. Another way is that tasks that require semantics. There's certain tasks that require that you really are predicting what you intend rather than just something correlated. And one of those is learning from textual description. And there we get a big increase in our accuracy. Another one of them is predicting unusual attributes on objects. If we're only learning things that are correlated, then we should be really bad at this. And indeed, when we use the whole features, we're not that great at predicting typical or atypical, or predicting unusual attributes. But we get a big improvement with the selected features. We can also look at localization. So in our ground truth, we only have attributes attached to bounding boxes, and there's no localization provided. So if we use all the features and try to train classifiers, we can back project from the features to see what regions of the image made us think that it has this attribute. So like in the top row, this area in green are the areas that made it think that it has a face. And in the center, the areas in the green areas is where what made it think that it has a furniture leg. And again, the same for skin. But after we do this feature selection, there's still some kind of spurious areas, but there's a much stronger concentration of that's actually on the face and on the furniture legs and on the skin. And this is the same for unusual objects. Here it's reporting that an attribute is unusual, and then it's reporting what's the region in that object that made me think it has this attribute. So it says this car has text, and most of the area is on the text of the Dunkin' Donuts. It thinks that this motorbike has skin, which isn't right, but it's able to find what's making it think that it has skin. And it thinks this person has metal on him because he's holding this metal tray. Now, it's not always this good at localizing, but it has no chance at this without explicitly trying to get rid of these correlations or be robust to them. We can also look at the correlations of the attributes themselves. Now, this is a little tricky to interpret. What I'm showing is the difference between the correlations in the ground truth attributes and the correlations in our predicted attributes. And these are in the new data set for the objects that it's never seen before. And ideally, we'd have a very strong peak at 0, and it would be low everywhere else, which would mean that our predicted correlations match the correlations of our data set. When you use the whole features, you don't do that nearly as well. You're often correlated because you're learning correlations that were present in the old data set and applying them to the new one. In the case of the selected features, we do a much better job at matching the correlation of the unseen objects. But it's important to note that better semantics or learning what you intend doesn't necessarily mean that you're going to get better numbers. So in this case, even when we're training on the Pascal classes and testing on the Yahoo classes, we get about the same performance in predicting the attributes. And that's because we're trying to decorrelate the attributes as much as possible, but some of the correlations that were present in Pascal will still be present in the Yahoo objects, and some won't.
Well, this is a little bit worrisome here. So getting hold of the attributes should, in the end, if you have a proper data set, should help you.
Getting what?
Basically getting better performance, right?
No, what was the first part that should help you?
Getting the attributes.
Learning what you mean?
Getting sense of the attributes, right? As opposed to not doing it. Doing what you're doing should help you.
Not necessarily. Like, take the example of eye and head. It might be a lot easier to predict that something has a head than that you can see something's eye. And so if in both data sets everything that has a head, every time something has a head, you can also see its eye, then you're better off, number-wise, you're better off just learning head and using that to predict the eye.
Well, you don't even know whether they're using eye to detect head. I mean, that's another, if you show them headless eyes, would they get head at all?
Yeah, I guess that would be, I don't know.
If you showed them the skin on someone's belly that doesn't have arm and leg attached to it, would they even know that it was skin? I mean, it's a sense in which you don't really know what your attributes are.
Well, that's why, and part of this, we're trying to tease that out by looking at whether it can predict something that's unusual. So the case of an eye that's not on a head, that would be kind of an unusual thing. And the only case when you can really get that right is if you're not exclusively using the head to predict it. So that's...
But in the kind of information theoretic way of thinking, the only attributes that you need are the attributes that help you do better. The reason we came up with the word I is that it's somehow helping us, because we don't have a word for the third wrinkle on the forehead, because it's probably not useful.
Mm-hmm.
Not in Russian, I don't know, maybe in but so it seems like the problem here is your data set, that your data set is not rich enough for the eye to be useful. It seems like if you had a rich enough data set, you should be seeing an improvement.
I think not if you had cases where you have things with eyes without heads, like you were mentioning, then that would probably be the case. But if there were, this is going to sound very derivative, if there were no correlations between the correlations of the two data sets, then what you're saying would be true. But even when you try to emphasize like cross-category generalization and cross-data set correlations, there may still be correlations and biases that are in common just because they're both taken from this same world. I mean, among other things. So the right, like you could ask, what's the right strategy to predict an eye? If you want to do that as well as possible, the right strategy is not just to look for the eye. You also really do want to look for the head and body and other things, and use that in combination with an eye detector. So,
Like, aren't you? I mean, one thing that strikes me about this is that you've got a kind of a finite data set, and you're kind of adding more and more labels to the data set. So, isn't there? I mean, just from like basic pattern recognition, shouldn't there be? You should require a sort of explosion in the amount of data that you need to really train up these classifiers. Given that, say, in the most extreme sense, when all these labels are completely independent of each other, you would need as many labels as there are data sets to kind of properly train this up. And so you're kind of trying to leverage here that these labels are kind of correlated with each other so I can kind of learn them. But as you add more and more labels, like more and more descriptions, don't you kind of exponentially require more and more data? So aren't you going to kind of hit a kind of a brick wall eventually as you add more and more descriptions?
If they were completely independent from each other, I think that's true. If you want to learn 1,000 things that are completely independent, then you need more data than if you have 10 things that you want to learn.
So the trick that you're kind of leveraging here is that these things are related, so I can try to work on a finite data set. But as you're trying to get more and more information, shouldn't you, like, in principle, require more data?
You may need more data, yeah. So here we have 10,000 objects, we have 5,000 images that we're learning from. Yeah, I don't see that as a big problem, though. I mean, it's just as you want to learn more things, you might need more examples to learn them. But that seems fairly natural to me. No, I mean, you have to have examples and you have to have supervision in order to do learning. So I think there's no free lunch there.
Yeah, all right.
So if we just look at training and testing on the same class, using the whole features, we actually do much better at predicting the attributes, and that's because to predict whether something has an arm, you can just look to see if it has skin, or if it has an eye, you look at to see if it has a face, or whether it has clothes, or well, clothes wouldn't work, but in any case, this problem that I've talked about a lot. Something that really struck me with these experiments is that most of the time this is all we look at. If somebody proposes a new method, we look at how well do they do it on the final numbers of the data set. And if they're doing worse, then we tend to assume that the method's not as good, or a lot of people would assume that. But you could actually be doing worse because you're doing the right thing, because you're being careful about what you're encoding. Or it could just be that you don't have as good of a representation. So it's important to be very careful about, and we haven't perfectly teased out this issue of whether or not we learn what we intend, but it's important to be very careful about it. Okay, so here's how we this is sort of my answer to this question. One way that we can get at this is to test out a sample, which we did by testing on different categories that were drawn from a different image search mechanism. A second way is to evaluate on an implied ability. If there's some task that you should be able to do if you really got it right, then you can use that to help see if you've learned what you intended. In this case, those tests are the localization, detection of unusual attributes, and learning from description. And a third way, which is not what we do here, but what we did in a paper with Santosh and Marshall and Alyosha and James, is look to see if it makes reasonable mistakes. So you can look to see if by adding more information you reduce the error and you increase confusion in a reasonable way, like confusion between cats and dogs, rather than between cats and background, then that's some evidence that you're doing the right thing. Okay, so a big feature effort is new data sets. In particular, we're going to be collecting a data set where we have many more object classes, a more carefully designed and comprehensive set of attributes, including comparative attributes and attributes that are not purely visual. So if we want to be able to infer things like, can I poke something with it, which isn't a directly visual attribute, but it's something that you can infer from things that you can see. And we want higher quality training images and some additional supervision. I also want to look at applying multiple strategies for predicting attributes. I've been talking about this, trying to directly go from image features to these attributes. But it's important to use a combination of strategies to also look at similar things that you've seen before and to use category information. And we want to look more at learning by reading and other non-visual sources for learning correlations of attributes. So in conclusion, the big point is that inferring object properties is the central goal of object recognition. And categorization is a means and not an end. We've shown that a special form of feature selection allows better learning of intended attributes, and that learning the properties of objects directly enables several new abilities that aren't possible if you're just trying to predict categories as independent predictions. In particular, we can predict properties of new types of objects. We can specify what's unusual about a familiar object, and we can learn from verbal description. And as always, but especially in this case, there's a lot more to be done. We've sort of just sketched out the problem in our minds and in a little bit of work here. But I think that this is an important area for future research. Thank you.
Any questions?
So, is there any way, or would it be possible to add a system relatively easily by which you could take your counterexamples, for example, your zebra that has text, and put that back into your system and say, learn from that and make that mistake less in the future anyway? Mm-hmm. Or would you have to put that back into your examples and relearn the entire system in order to do that?
So could we do like active learning, that sort of thing, or online learning? Yeah, I think that's an interesting area. That's an interesting area of research. And also, if you're trying to learn categories, it would be nice if the computer would not just say, this is a dog just because, but say, I think this is a dog because I think here are the legs and here's the eyes and so on. And then you can make specific corrections to improve its ability to detect things. So I think that's something that could be done, yeah. I think you're next, yeah.
So there's an underlying issue here, I think, that see, what you really want is a sort of a gestalt recognition. I know that's a discredited word in some circles. The features aren't really defined until the thing is defined, and that helps to define the features, but the features help to define the thing. So you've seen that face where the face is made out of two apples and a banana and a strawberry or something. And those become eyes and mouth once you decide it's a face. Mm-hmm. And somehow the whole picture has to snap out at you at once. That can be done by iteration. It can be done by sort of something that combines top down and bottom up simultaneously.
Sure.
Probably can't be done as a pipeline that goes in one direction.
Sure.
Because the features and the thing that they're a part of co-define each other. So I think again, you can start off with things that are strictly unidirectional features like shiny or round.
Mm-hmm.
But I think what's bothering a lot of us is when you get into wheel, that only makes sense in the context of things that have wheels, and yet you're trying to use them to identify things that have wheels. And round you go.
Yeah, so also there's a few points about that. One is that I'm not as concerned, once I know something has wheels, I don't care so much what I call it. If I know it has wheels, and that's useful information in and of itself. Another thing is, I agree, I'm not actually proposing this as a unilateral way of trying to infer things. Like, I'm not advocating a bottom-up strategy for inferring things about the scene. I'm saying that what I am advocating are shared representations and being very explicit about what you're trying to learn. And I'm perfectly fine with, I would be also fine with the strategy of saying, you recognize that it's a face, and so therefore it has these attributes. I think it's just important to be aware of the limitations of that and to make sure that you know what you're actually learning.
Thanks.
Mm-hmm.
So I listened to what you said, and I thought that it was 30 years ago, and you said, I'm going to do a blackboard system, and I'm going to have assertions at many levels, and we're going to sort of interact with each other, and that's how my thing's going to work. And it's very interesting to me that we're sort of recapitulating what has gone on in speech recognition. I was wondering whether you agree that we're back to 30 years ago, or maybe not.
No, I don't. I don't think so. So a lot of things have changed since then, obviously. One is that we have better ways of representing. We have better feature representations. We have a lot more data. We have machine learning algorithms and better ways of. We have very flexible ways of learning about the relations of things. Like we have learning with structured outputs and graphical models and various ways of dealing with these problems. So we're much better suited for doing the kinds of things they were trying to do then. But also this isn't the kind of thing they were trying to do then. So the idea of a lot of some systems of the 60s would be that you detect like this is like a oval brown region. This is like a rectangular brown region that must be a tree trunk, and this is sort of a blobby green thing, so it must be the tree leaves. And you sort of have a cascade of brittle processes, and then hope that at the end of this, you've formed it into some kind of coherent scene. I think it's very important to be aware of the pitfalls of that idea and of going in this direction. But I don't think that the traps that they fell into are inevitable. Yeah.
So you're going linguistic, so why don't you go whole hog and use word occurrence numbers and word co-occurrence numbers to help you sort out which features co-occur. In other words, in the linguistic domain, presumably the covariance matches the covariance in the image domain.
Yeah, I was talking to these guys about this. I think it was, actually I forgot what your first name is, Mark and Dean. So I was talking to Mark and Dean about this. They're working on sort of predicting new words based on attributes from like fMRI and from images. So it turns out that the correlations in the linguistic domain are not very predictive of correlations in the visual domain. That's one answer, and that's something that I think they found to some extent. So that wouldn't necessarily be a great way of going, but there are other sources of learning about things that you can apply to vision. So you could learn. You don't necessarily want to have to observe a million things driving that have wheels to figure out that if something has wheels, it can probably be used for moving around. So I think that there are things that you can learn from text, but it would be a little naive to just take co-occurrences from websites and then apply them to visual data.
I think the problem might be that the obvious things are not written down.
That's a huge problem, especially if you're trying to attach words to images or learn from text surrounding images, but it's a little different.
Even if I came to you and I said, here, I have an information source that basically has 10% correlation with what you care about. That's a huge amount of information. That's very valuable.
Yeah,
so
yeah, I
don't
agree.
think they have to be the same. And I don't think they have nothing to do with each other.
Yeah, it's an important source of information, and you just have to be a little careful about how you use it.
Any other questions? Okay, well,
here's a question.
Oh, here's a question. Okay.
I think attributes should only include those things that are very basic, very fundamental. For example, round or shiny. I don't think it is helpful to include something like head or wing or leg into attributes because there is a huge variation in those attributes.
Sure. So I guess there's two questions. One is how should we turn our pixels into good image features or good image representations? And there's another question, which is what is it that we should be trying to predict from the images? And this is a statement that what we should be trying to predict at the end are things that are not visual. I think the goal of vision is to move from something that's purely, move from visual sensing to something that has, whose meaning is not visual in and of itself. And so I guess, so that's why I think this isn't necessarily the best you don't necessarily want to predict these attributes and then use them as features for everything else. I'm saying that these are the kinds of things that you want to know at the end of the day.
All right. Any other?
There's one over here.
All right.
One small question. From going from your attributes or your description, when you go to the object category, what kind of model you are using? What is? It's
just a nearest neighbor based on the description, which will be basically a binary attribute vector, and the predicted attributes.
Okay, so there is PSR in the next room that is, I think, should be set up by now, and there is going to be drinks there. So we will just slowly migrate there, and Derek will be available to answer more questions in a more friendly atmosphere. Let's thank him.